Section 14.2, Measures of Spread. So in the previous section we looked at measures of center, which would be the mean, the median, and the mode. Now we're going to switch to looking at the idea of how spread out a data set is. So the first measure of that we're going to look at is called the range. So one option for measuring the variation or spread in a data set is to calculate the distance between the largest and smallest data value in the set. And this is referred to as the range of the data set. So just to get a sense of how spread out something is, you look at the value on the right, you subtract the value on the left, largest value minus smallest value, and you see just how far apart those are. So let's look at that in this example. Suppose that we randomly sampled 5 statistics students from California and 5 statistics students from Texas, and then we asked them how many people live in their household. Their responses are illustrated in this graph. So we see in Texas, one person, there was 3 people in their household, another was 4, 6, 8, 9. In California it was 2, a couple 4s, 1 5, and an 8. So which data set appears to the eye to be more spread out, California or Texas? So one of the things that catches my eye is that for California we have 3 values that are very kind of tightly packed together, whereas here things are more spaced out overall. So by eye, because of this cluster in the middle, it seems to me like, let's see, which one is that? California is less spread out. The more spread out one is the one where they're spaced all apart, which seems like Texas. So my answer would be Texas. More space between the data values. They didn't ask to explain, I guess, but that's kind of what caught my eye. And I don't need to write too much here, given they didn't ask us to explain, but also the cluster in California is what made me think that one was less spread out. So now they want us to calculate the range for the observations from each of the 2 data sets, and the idea would be to see if that matches what we saw by eye. So I'll do a range for Texas, so I'll call that RT. That'd be the largest observation in Texas, which was 9 people in the household, minus the smallest observation we got, which was 3 people in the household. So the range there is 6. And then if I do that same calculation and do the range for California, the largest number of people per household in my sample was 8, minus the smallest observation, which was 2, and I actually get 6. So according to the range, those are both spread out the same. But when we thought about it by eye, and hopefully you agreed with me, Texas seemed to be more spread out than California did in terms of the way those dots were distributed on the graph. So the question that kind of naturally follows from that is, why does the range fail to match what we see with our eyes? And my answer is fairly simple to that, which is that the range only considers 2 of the data values. So what that ends up meaning is that if things are spread out differently in the middle, we don't notice that. So the distance from small to large was the same in Texas and California, but the middle 3 here were very tightly packed together, whereas the middle 3 in Texas were more spread out, but the range only uses the largest and the smallest, so it doesn't notice what's going on in the middle. So the range is nice because it's a really quick calculation, but it does have that drawback of not paying attention to what's happening in the middle of the data set, and we do care about that a lot of times. So we need a different calculation that'll help us detect that, and that's going to be called the standard deviation. Our focus on this class will be on data sets that we consider to be samples, so we'll start off looking at the sample standard deviation. And the sample standard deviation is a number that measures the overall variation or spread in a data set. Notice the word overall, right? Not just using 2 values, but the sample standard deviation is going to use all of the data values when we make our calculation. The formula is a little scary looking. It says the sample standard deviation will be S, so that's not scary, but that's the symbol we use for sample standard deviation. but this is a little intimidating. It says that to get S, we need to take the square root of the sum of the squared deviations from the mean divided by 1 less than the sample size. This, the way it printed, is a little weird. That's an X bar and then an N parenthesis. It looks like a parenthesis goes up over the X, but it's a separate bar on the X that happens to be touching the parentheses. All right, so how do we do that formula is a very fair question. How would we make that work? We have an example on the next page, so we'll go ahead and look at that example and see that this isn't quite as bad as it might look at first. All right, so as we turn the page, they want us to calculate the mean and standard deviation for the California sample using the formulas. So the mean with the formula from 14.1 and the standard deviation with the formula that we just saw on the previous page. So I'm going to write those two formulas down. The formula for sample mean is X bar equals the sum of the different X values divided by the number of X values. And the sample standard deviation that we just saw on the previous page is the square root of the sum of each X value minus the mean of all the X values, which will have come from up here, squared. So that's what that should have looked like on the previous page where those aren't touching. And then divided by n minus 1. So let's go ahead and see how that works. I think that the best plan here would be to make a table. So I'm going to list the X values in that table, and those would be the X values for California. So I'm just going to look through this list. We have a 2, a couple 4s, and then a 5 and an 8. So I'll put those in the table. And the first thing that I would need from that is the sum. So we just bring in the calculator real quick and add those up. 2 plus 4 plus 4, that's 10, plus 5 is 15, plus 8 is 23. And then the X bar value would be equal to that sum divided by the number of data values, which is 5. So 23 divided by 5 is 4.6. So there's the mean household size for California, at least for that sample of 5 students' households. And now we want to get to this. So here's the key. Notice that I added the x's to get the 23. That was part of this process. I did that because the x's had a sigma in front of them. So what has a sigma in front of them in this formula is the x's minus the x bar squared. So when you're trying to calculate something by hand and there's a sigma, in your table, whatever comes after the sigma, make that a column heading. So we're going to try and take for every x value, we're going to subtract the mean from it and square it. So I'm going to go ahead and show you that in steps. So our first x value is 2 minus the mean of 4.6 is negative 2.6. And it turns out that if you didn't square this, which we're going to do, so I'll square that and get 6.76. But if you didn't square it, then the negative and positive values would end up canceling each other out and you would get a sum of 0. So if you want to really measure these deviations or distances, you can't have them canceling out if you want to get some sort of average deviation or total out of there. So we square to get rid of the negatives so that when we add up, they don't cancel out. So just showing you another one, 4 minus 4.6 is negative 0.6, and we square that, we get 0.36. So the next one is the same x, so you'll get the same answer, but I just want to go ahead and calculate it again anyways to show you how to do it all at once. So we can just type just like we see here, open parentheses, the x value we're dealing with right now is 4, minus x bar, which is 4.6 on every line, end parentheses, and then square. And if I do that, then I get the same answer as I did before, but all in one step. And one of the nice things about doing that is when I go to the next line and I need a 5, I can just hit second enter, pull up that last one, change the x value to a 5, and get the square deviation, second enter again, make that an 8, and get the deviation squared for 8, so 11.56. Alright, so that's a big part of calculating S. That's the biggest part probably. Now we want the sum. So I'm going to drag this back in for a moment and add all those up. So 6.76 and so on. and we get 19.2. And once I have that, I'm ready to calculate S. S is the square root of that sum, 19.2, divided by n minus 1. So n was the number of data values, which is 5. So 5 minus 1 would be 4. I don't want to really write 5 minus 1 because I would need extra parentheses in the calculator to do that, but that came from doing 5 minus 1, the sample size minus 1. And then I'm going to go ahead and enter this into the calculator and get the value of S. So I would do the square root of 19.2. Don't end the parentheses because then you would only take the square root of the top. So divided by 4 and then end your parentheses so it does the division first and the square root of that whole answer. And we get 2.190. It's an 8 but followed by a 9, so I'll round that up and make it a 9. So in my stat classes we always use 5 significant figures on our standard deviation, so 1, 2, 3, 4, 5. I think in my math lab they'll ask you to use less, so go ahead and follow their directions. But this is what you'll see me do most of the time is 5 because that's the way we do it in statistics. Alright, so now they want us to calculate the mean and the standard deviation for the Texas sample, but this time they want us to use the graphing calculator, which is nice because if we do that, we can have the calculator basically do all of this work for us, and the only thing we'll need to write down is X bar and S, and we can go just straight to those answers without really having to do any work on our own in terms of tables and formulas. So let me show you that by bringing in the calculator. So what we want to do is enter the data for Texas in. So I'm going to hit Stat, and with Edit highlighted, press Enter, just like we've entered data before. And I'm going to enter the Texas values. So it looks like a 3 and a 4, another dot at 6, and 8, and 9. And that's basically most of the work. Now I'm going to have the calculator do the rest by just knowing how to ask it. So what I want to do is hit Stat again and go to the Calc menu just like we did for regression and other things. But I'm just going to go with the very first option here, one variable statistics, and it wants to know what list, so notice the cursor still flashing there. So I'm going to hit second L1 to let it know that I want it to do one variable statistics for the data that's in L1. And when I do that, notice that the X bar is given, so X bar is 6, and then the value of S is given as well. So S is approximately 2.5495. So super fast and simple. With a little practice you can do that pretty easily. Let me just show you the California ones, and that'll kind of double check our work here as well. So if I go to Stat and Edit, clear out Texas, put in the California data, Stat, Calc, one variable statistics for L1, we get an X bar of 4.6, and then our S, 2.19089, but if we rounded it would be a 9. So in Stat, you'll learn this a little bit again, practice by hand and calculator, focus on the calculator, and in here we're going to focus on the calculator as well too. So I want you to see what the process looks like by hand, but we'll focus on doing it with the calculator, especially as data sets get larger. Alright, so now let's see what that's used for. Does the standard deviation produce results that match our decision about how spread that the data was that we made when we were just using our eyes? And explain. So let me bring that paper back in. When they asked us to do it by eye, I said Texas looked more spread out. So how is this a match? Well, it turns out that when the standard deviation measures spread, the way that works is the bigger the number, the more the spread. So I thought Texas was more spread out, and notice its standard deviation is a little bigger than the standard deviation for California. So let's write that up. Does the standard deviation produce results that match our decisions? Explain. So first of all, yes, it does. And explain. Texas had a bigger standard deviation. And standard deviation measures the overall spread of a data set, so a larger standard deviation means more overall spread. So it is a match. All right, so let's go ahead and summarize a few things from the standard deviation. The sample standard deviation measures the typical distance from the mean. So notice that at the center of our formula is take every x value and subtract the mean. When you do the difference between two values, you're doing the distance between those values. And so we did the distance between every x value and the mean, and that helps us find the typical distance from the mean. And the greater the spread or variation in a data set, the larger the standard deviation will be, and that's why when Texas was more spread out in the data, it produced a larger standard deviation. And then the mean, median, and standard deviation can all be computed quickly and easily using a graphing calculator. Just enter the data into L1, choose Calc and one variable statistics L1, and you'll get all of those answers. So if I bring in our results for California again, here's the sample mean, and here's the sample standard deviation S. We have the total of the x's. Some other things we don't usually actually use, the sum of the x squareds or the sigma. You'll learn more about those in stat. But if I arrow down, it also gives the minimum and the median and the maximum, as well as a couple things referred to as quartiles that you also learn more about in stat. But the median is there as well. All right, and then there's one other number the calculator doesn't give, but you do get asked for it in my math lab sometimes, and that would be s squared, and that is referred to as the variation. The variance of a data set. So the variance of a data set is something we usually use in more higher level theoretical statistics classes. The standard deviation is something that gets more use, but they do ask for it at times in my math lab. So what you'd want to do if they asked you for that is just have a look at your S, type 2.19089.023, square that, and there is S squared. So you can always get the value of S by just taking, or of the variance by taking the value of the standard deviation and just squaring it. I won't ask you for that probably on tests, but it does come up in my math lab sometimes. And then the idea visually for this one right here, so the more spread, the larger the standard deviation. So when we have a larger standard deviation, the data is spread out wide. When it's smaller, we would have our data spread out narrow, or think about what the histogram would look like. So if you had two groups and one was spread out more than the other, you would see that in the standard deviation through narrower and taller is less spread out, and shorter and wider is more spread out, but the standard deviation will reflect that by larger standard deviations being more spread out or higher variation, and small values of S meaning less variation, less spread, and that'll be narrower and taller. And we'll look at that in some histogram problems coming up. Okay, let's go ahead and look at another example. The table below shows the 2013 tuitions in dollars of 10 randomly selected four-year public colleges. So we have a random sample of public colleges. So when they ask for the mean, they want the sample mean. When they ask for the standard deviation, they want the sample standard deviation. So our first task here is to figure out x bar and s for this sample. I suppose we could do it by hand like we did for the California data, I think it was. But these numbers are messier and there's more of them, so it would be not as nice to do it by hand, and we have a simple option of doing it on the graphing calculator instead. So I'm going to choose that. So I'm going to press Stat and Edit and clear out the old value there, the values there from California, enter the new ones in. It doesn't really matter whether you go down or across. What matters is that you get every number in there exactly one time and that you don't have any typos. I generally like to work in the vertical fashion, but again, it doesn't really matter. It's kind of good to check to make sure that L1 of 10 and there was 10 values there, just to make sure you didn't miss anything. And then once you've entered that in, it's just Stat and Calc. Choose one variable statistics, which is already highlighted, so you can just press Enter. And then second L1 to let the calculator know where to look in the list. And then we get our X bar, 6,480.30. it's money, so I'll add the extra 0 just to make it look like money to the nearest penny. And then the standard deviation, 2342.76, also would be measured in dollars. Throw the commas in there. So we have a mean of 6,480 for the public schools in our sample, and a standard deviation of about $2,342. I said that we use 5 significant figures for standard deviations, and I did 1, 2, 3, 4, 5, 6 here. The rule is actually at least 5, so I could have just done 5, but because it was money, it made sense to me to go 1 extra digit to get to the nearest penny. So when we have the graphing calculator around, getting means and standard deviations should be no big deal. So we're going to want to spend most of our time thinking about what those mean. So this is the mean and standard deviation for this sample of 10 public colleges. Now they say, suppose that we took a similar sample, but this time it was for private colleges, and that the mean of those, X bar, turned out to be $20,650, and the standard deviation, S, turned out to be just over $10,000. So which sample of colleges has the higher typical tuition? So the thing you want to think about there is what's a better measure of typical tuition, X bar or S? So X bar is a measure of center, which makes more sense for the word typical. Standard deviation is a measure of spread, so I wouldn't use standard deviation to measure which one had a higher typical tuition. I would use the mean. I would also be willing to use the median, but because they just gave us the directions to find X bar and S, I think makes sense to take advantage of what we are given, so I would use the mean, and then I would answer that private colleges have typical higher tuition because the average for the private colleges is much higher than the averages for the public colleges. So my first part of my answer would be private, right? Which sample of colleges has the higher typical? It was private. And why? Because it had a larger mean. 20,000 compared to 6,400. And then which sample of the colleges has more spread? So the mean does not measure spread, but the standard deviation does. So which one has more spread? S for the private ones is 10,000. For public it was only 2,300. So again, I would say that it's private. It's just this time my answer would be because it has a larger standard deviation. So we're getting these values nice and quick from the calculator, but what are they used for? The mean could be used as a measure of a typical cost. The standard deviation would be more of a measure of which data set was more spread out. So it looks like in these samples that the private colleges have a higher cost and are more spread out. We do have to keep in mind though, this is just a sample. So when they ask down here, can we say that in general, four-year private college tuitions have more spread than four-year public tuitions? And explain. What they want us to say here, I think, is no. I kind of disagree with that a little bit, but I would say to follow what they want, no. And my reason would be we only looked at a sample of 10 colleges. And I believe that was each kind, yeah. We looked at 10 of each. So it could be different in the population. So in the sample, it's definitely the case that the private colleges were more expensive and that they had more spread. But can we say that there would be more spread always between the private and the public? Not necessarily. Now I said I kind of disagreed with that answer, so I'll write my answer here in a different color. If I was asked that question in a stat class, I would say probably. Even though I can't be certain what's going on in the population by looking at a sample, it does give me an idea. And when the difference is really big, 20,000 compared to 6,000, it's unlikely that that difference is just a random fluke. It's probably a real pattern. So I would say probably, because the sample mean for private was much larger than for public. So samples aren't worthless. Samples do give us an indication of what's going on in the population, and there can be a little bit of error in those samples, but not usually too much. So when I see such a big difference between the sample mean for private versus public, I think that kind of shows me that private really is more expensive than public, not just in the sample of 10 schools, but probably overall. It would be really unlucky for us to get results like this in our samples if the truth wasn't like that among all private and public colleges. So my math lab encourages you to say no, because they want you to realize that a sample isn't the truth, it's just an estimate. But it's a pretty good estimate, so when the estimate shows a big difference, you can be pretty confident that that difference really exists in the population. But answering that question involves more statistics. So for now, we can't be sure, but I'm telling you it's probably true, and if you take me for stat, I'll show you why. One of the nice things about standard deviation is when it gives us a typical distance away from the mean, it gives us a sense of how much data will lie within 1, 2, or 3 standard deviations in a lot of different types of data sets, even if the data sets are about very different things. So they might be about college tuition costs, or they might be about the number of people that live in a household. The examples we looked, even though those are very different, the empirical rule says that there will be some things in common to those data sets if we measure and count things in terms of how many standard deviations away from the mean they are. And this idea is summarized in something called the empirical rule. And it says if a distribution is unimodal and roughly symmetric, which is like a bell-shaped distribution, then the following statements apply. Approximately 68% of the observations lie within 1 standard deviation of the mean. That is, they lie somewhere between x bar minus s and x bar plus s. So 68% roughly lie within 1 standard deviation of the mean. If you ask what percent lie within 2 standard deviations of the mean, you're going out twice as far on both sides, and it turns out to be about 95%. If you were to go out 3 standard deviations, by then you get almost all the data, and it ends up being approximately 99.7%. So that, again, turns out to be true for what percentage of public college tuitions lie within 2 standard deviations of the mean? Probably about 95% of them. What percentage of household sizes lie within 1 standard deviation of the mean? Probably about 68% of them. So this rule will apply despite whether the topic is about small numbers like household size or big numbers like tuition size, or even totally different topics. As long as it's unimodal and roughly symmetric, you should get answers pretty close to these. And 2 key consequences of the empirical rule is one of them is any observation that lies within 2 standard deviations of the mean is considered to be in the expected range of data values. So this 95% of the data that's kind of in the middle, we say if you lie in that hunk, that's the kind of things we expect to see in the data set. But any observation that lies more than 2 standard deviations away from the mean is considered to be an unusual observation. So that's a big question in statistics. When we see a data value, we look at it and think, is that something we expected to see, or is that a surprise or an unusual data value? And the cutoff for which way we describe that is 2 standard deviations away from the mean. So we'll look at that a little bit in the upcoming examples. All right, so let's take a look at this example here. Which of the histograms below could represent a data set with a mean of 40 and a standard deviation of 2.6? So let's see. First, which ones could be a mean of 40? For a symmetric data set, the mean would be near the peak. So this one looks like a mean of 40 is possible. This one looks like a mean of 40 is possible. Here, 40, there's no data around that, so I can rule that one out. And 40 here is kind of where the data is, but you can't have the mean have all of the data to its right. It's got to be a balancing point of data values on the left and the right. So this one doesn't make sense either. So both of these seem reasonable to me that they could have an x bar of 40. So I've narrowed it down to two options, A or C. So the empirical rule will help me do the other part. For the standard deviation of 2.6, let's do 40. Let's do x bar plus or minus 2 times s and see what we get. This is not a 5, but an s. And let's see what numbers we get for that. So x bar would be 40 plus or minus 2 times, they said the standard deviation was 2.6. If I do that with the minus, let's see what I get. 40, let's clear this out. 40 minus 2 times 2.6 is 34.8. And if I do that calculation with the plus sign, I get 45.2. So according to the empirical rule, if you go 2 standard deviations to the left and 2 standard deviations to the right, then the percentage of data between should be about 95%. So let's think about that on these pictures. If I go to 34.8, that's right about here, and 45.2, that's maybe right about there, does that look like 95% of the data? And I would say no way. There's a lot on the right, there's a lot on the left. This is not the majority of the data. But on this graph, if I went to the 34.8 and the 45.2, almost all of the data is in the middle with just a little sliver over here on the right and a little sliver on the left. So it seems reasonable on this picture that the middle might be 95%, like the empirical rule says should happen within 2 standard deviations. And then those little slivers on the outside could be the other 5%. So I think that I have to rule this one out because it doesn't look like it has 95% within 2 standard deviations. This one, that seems reasonable. So I would bubble in that choice right there if I was answering this on my math lab. So that gives you a little bit of a sense of how the standard deviation can help us detect which graph is which by thinking about the spread and thinking about the empirical rule. All right, let's look at one final example on standard deviation that uses a density histogram. So a density histogram of the heights in inches of women at a large company is displayed below. Remember that for a density histogram, the area of the bar, which they've filled in on most of these bars for us already, represents the percentage or relative frequency of women that would be in that category. So estimate the proportion of the heights that are between 60 and 68 inches. So 60 is here, 68 is right there. So we just want to add up all the ones that are in between. Remember those areas that they put represent proportions or relative frequencies. So we have 0.14 plus 0.20 plus 0.20 plus 0.14, and I get 0.68 or 68%. So what they would like to have happen in our mind is that we see that 68%, we think about the empirical rule, and we think, ooh, that's the one standard deviation amount. So probably when I went out from 64 to 68 and from 64 to 60, that was probably going out one standard deviation because the percent or proportion there is 68%, and the empirical rule says if you go out one standard deviation away from the mean, you should get 68% of your data. Now they want us to do the same thing for 56 and 72. So if I go out to 56 right there and 72 right there and counted everything in between, then I would have the 0.68 that I already had. And then on the left, I would pick up these two bars right there, 0.04 plus 0.10, and the same thing on the right. Looks like we have a symmetric data set here. And when I add those up, I get 96%. Get 0.96, but that is 96%. And that's not quite what the empirical rule says would happen within 2 standard deviations, but the empirical rule said it would be about 95%. That seems to be about 95%. So because that's close to 95%, that should make me think about 2 standard deviations away from the mean, according to the empirical rule. And then estimate the sample standard deviation. Well, it looks like this number matches up with 1 standard deviation, and this matches up with 2. For symmetric data sets, so they didn't ask me to estimate the mean, but I kind of need it, so let me write x bar first. X bar on a symmetric data set would be kind of that point of symmetry, which is right here. That's kind of where the mirror imaging is. So it looks like the mean is 64. And then I'm claiming that if you went out 1 standard deviation, you should get 68% of the data. So how far was it from 64 to 68 and from 64 to 60? In either of those cases, that was a distance of 4. So it looks like S is probably about 4. And then what if I use the other one with the green line? The distance here from 64 to 72, that should be about 2 standard deviations. And the distance between 72 and 64, you can subtract, 72 and 64 is 8. But because that's about 95%, I would think that distance represented 2 standard deviations, and when I divide by 2, I get 4 again. So they're wanting us to use the empirical rule to think about this is about 1 standard deviation's worth of data, so how far away from the mean did we go? Well, from 64 to 68 is 4 units, so that should be 1 standard deviation. The 96% is close to 95, so that distance should be about 2 standard deviations. And the distance from the center to that cutoff they gave is 8 units. Divide that by 2, because 2 standard deviations, and you'd get 4. A little tricky, takes some getting used to, but that's the idea. And now let's answer some other questions. If women that worked at this company, I think that means if a woman that worked at this company was 74 inches tall, would she be considered unusually tall at this company, and explain? So what we need there is that idea from the previous page, that if this height is within 2 standard deviations, it's expected, but if it's outside of 2 standard deviations away from the mean, it's unusual. So where was that cutoff? It was at 72 inches, so 74 is outside of that. So there's a couple ways that I could do that. One is just by eye. I would argue that I'm thinking this range from here to there is the expected range, and that everything on the outside over here would be unusually tall, and over here would be those that were unusually short. And the 74 falls in the unusual range. If you had just the X bar and the S to go by, then the other thing you could do is do the math on that and say the cutoff for unusually tall is X bar plus 2 times S, which would be 64 plus 2 times 4, which is 72. So when we notice that she's above 72 inches tall, we would say that it is unusual. So would she be considered unusually tall? Yes. And then why? Because she's more than 2 standard deviations away from the mean. And I guess we'll say above the mean to focus on the tall side. All right, here's 2 standard deviations away from the mean is 72 inches. She's 74, so she's even taller than that, so she is unusually tall. What's the expected range for the heights of the women at this company? Well, we already kind of have it labeled up there on our picture. It's anything from 56 inches to 72 inches. The computation for that, if you didn't have the picture, would be to do X bar plus or minus 2 times the standard deviation. Again, that's an S, not a 5. So that would be 64 plus or minus 2 times the standard deviation, which is 4. That's 64 plus or minus 8. When you subtract, you get 52. When you add, you get 72. Did I do that right? No. When you subtract, you get 56. And when you add, you get 72. So the expected range is between 56 inches and 72 inches tall. Anything in between that's an expected height for a woman at that company. Anything outside of it is either unusually short or unusually tall. No judgment there. We're just saying it's rare when we say it's unusual. We're not saying if it's good or bad. And then finally, what proportion of the women at this company are shorter than 56 inches tall? So we're going to have to use the complement rule to tackle this one. So what proportion of women are shorter than 56 inches tall? Let me go ahead and highlight that in red. So there's 56 inches. So that would be those women right there. Notice that looks to be the same as this side right here. And we do have good symmetry everywhere else in this graph. So I'm going to take it to be true what I see by eye there, that the left and right hand sides are the same. And here's the math that I'm going to do on that. I know that the total amount of area for a density function is 1. And if I subtract out the 0.96 that we got in the middle, I get 0.04. So one of the things I know about a density histogram is the total of all the bars is 1. I've already calculated the area of the ones from here to there, and that was 0.96. So I get this 0.04 left over, but that's not the answer to the question, because 0.04 isn't the area on the left, it's the area on the left and the right combined. So if I just want the area on the left, I need to take that 0.04 and I need to cut that in half, and that would be 0.02. So I would guess that the proportion of women at this company that are shorter than 56 inches tall is 0.02 or 2% if they ask you to interpret it as a percentage. So again, if we went to the graph here, let me just pull in another color. In between the 56 and the 72, we already calculated that that area is 0.96. So what I'm claiming is out here is 0.02, and over here is 0.02, and that makes sense because if you add it all up, you get a total of 1. All right, so that wraps up section 14.2.